Hi everybody. Just wanted to go ahead and film a video that lets you see the answers to your different homework problems over chapter 5. This first video is going to go over the first 5 questions. The second video is going to go over the second 5 questions. I apologize in advance if this is choppy, because I'm having some problems with my voice. I may have to pause and take a drink and then come back to things. So if things are choppy, I do apologize in advance. It's because I don't want you to listen to me hacking. For that specific purpose, I'm gonna go ahead and I'm gonna get started. Number 1 asks you what is meant by the term system in thermodynamics. And what I do want to remind you of is that a system is defined as the for us, products and reactants of a single reaction or a series of reactions. Products. Whoa, productants is not a word. Products and reactants. For us, what that means is that anything within the reaction has an impact on the reaction itself. Anything outside of the reaction is typically referred to as the surroundings. So that was the answer to the last part of this one. The middle question asks, what is a closed system? Closed just typically means in a contained area. So if we took our beaker chemistry and we put it in a system where nothing could get in or out, think like a big vacuum of, whatever proportions. If nothing can get in and nothing can get out, then that system is technically closed, and whatever heat it produces stays within, and whatever energy is produced stays within, and so on and so forth. For us, we're going to focus on this idea of a system so that we can determine how reactions are either exothermic, endothermic, so heat producing or heat releasing, or heat absorbing, and endergonic and exergonic. Remember that ender means given away, so energy releasing or energy gaining for exergonic. That being said, please do understand that, like, when we talk about these, typically we just focus on exothermic and endothermic. All right, from there we're going to go on to work. In number 2, work is defined as the force that is applied over a distance in order to make something move. For us, what that means is if we wanted to calculate work, we would need force and we would need distance. And the other thing that kind of goes hand in hand with work is going to be heat. Heat is denoted by Q. We typically measure as a change in temperature. And remember that from previous courses, you've learned that temperature is related to kinetic energy, and that however fast the molecules move is related to how high the temperature is. For us, when we talk about heat transfer, heat only transfers from hot objects to colder objects. So heat is like this force or this presence that is moving from a hotter object to a colder object always, never the other way around. For number 3, I went ahead and I added this table from our lecture that had to do with the sign conventions for Q, W, and E. Because for number 3, your goal is to figure out what delta E is by adding Q and W together. But in order to do that, you need to be able to identify the sign on Q and W. So for part A, we're going to do part A of most of these. And what we're going to see is that there is a balloon that is cooled by removing 0.655 kilojoules of heat. Since the system is going to be removing heat, it means that it's going to lose heat specifically. So that means that the sign is going to be a negative value. And this is going to be for Q. Okay. The other thing we're told is that the work that is done on the balloon, the balloon is the system here, what we're going to see is that the sign of W is going to be positive. And we were told it's 382 joules. Now, the problem here is that our units are different. So I'm going to go ahead and I'm going to convert my joules to kilojoules by dividing by 1,000 so that everything is in the same unit. And for us, we know it's going to be a positive value. Now that we have the negative value and the positive value, we have delta E is going to be Q plus W, which equals negative 0.655 plus 0.382, and that's going to get us a negative 0.273 kilojoules of energy. Now the other thing that we need to also determine is if the process is exothermic or endothermic. Since over the course of this process, the system itself is actually losing energy from the system to the surroundings, we would refer to that as an exergonic system. When it comes to heat, since we're talking about exothermic and endothermic, we would also then define the system as exothermic because it is again releasing energy from the system into the surroundings. And so that's how you're going to go through and you're going to do different things. In part B, one of the things to note is that work is 0 because you're not told anything is doing work or anything along those lines. And then you're told in part C just the amount of work. So you would have to assume in part C that Q equals 0. Okay. Yeah. All right, so part A, we have a couple of equations that we can use, but for this particular thing, it's asking you, why is it easier to measure change in enthalpy than the change in internal energy? And your book goes through and derives this particular thing, is that delta H is just equal to Q. So it's a lot easier to measure changes in Q because we have information that help us do that, like we have the calorimetry experiments that give us mass times specific heat times change in temperature. We also have gone through and equivalated that any change in heat is related to enthalpy specifically. Measuring internal energy, the equation, the equation is going to be a rearranged version of this. In order to measure internal energy specifically, we would need information about the actual equation. And this all had to do with the fact that Q plus W and work was related to the change in volume times pressure in a constant pressure system. In part B, whereas H is a state function, Q is not a state function, and that would have to be you trying to remember that a state function does not depend on the path taken. So for instance, for delta H, we can use Hess's law to do several different equations added together to get an overall delta H of the total reaction. And in the case of Q, we would actually need to measure initial and final changes, and we'd need to know exactly how much and things of that nature. So Q is not a state function primarily because you need to know amounts and specific heats in order to calculate it. And for part C, it says that for a given process at constant pressure, delta H is positive. Is the process endothermic or exothermic? When H is positive, the system is defined as endothermic. And that's from our lecture. All right, one more, and I'm going to take a break. You are given delta H for a process that occurs at constant pressure. What additional information do you need to determine delta E? And I'm going to take you back to this equation that says delta E plus P delta V will get you delta H. If you're given this, and you know that this is a constant pressure, in order to calculate delta E, you would need delta V, so change in volume. All right, that's it for this video. When you are done viewing this one, go back and double check your work, make sure you've gone and interpreted some of these concepts correctly, and then we'll go ahead and we'll get started with video number 2 with numbers 6 through 10 here shortly. All right.